So page 5. Okay, so we know there's something a little strange about these functions, right? With that radical, it doesn't have to be in the numerator, it could be in the denominator as well. Okay, so we know that horizontal asymptotes relates to limits approaching infinity. So we know that if we're dealing with infinity, we know we're comparing degrees. So if we're comparing degrees, what does that show us here? Are they same or different? Same. Good. So that square root is going to force that x squared to go down to degree 1. So top is degree 1, bottom is degree 1. So as we approach infinity, what's going to be the limit here? Yeah, -2 over root 6. And what do you think is going to happen if I do limit x approaches negative infinity for the same function? The same ratio, but what's going to happen with the signs? It's going to become positive, right? So we talked about how normally that's not the case, right? Normally for rational functions, it's the same asymptote on either side, but if there's radical involved, imagine inserting -100 into the numerator here. This will give us positive divided by a positive, and that's why we get positive. So anytime we see the degree being the same and there's radical involved, you know there's going to be two horizontal asymptotes. So we can say our asymptotes are y is equal to 2 over root 6 and y is equal to -2 over root 6. Now you could rationalize the denominator, but for AP exams, they don't care about rationalizing the denominator. So you can leave radicals in the denominator, and that's perfectly fine. Okay. Number 4 is just review, so we can skip number 4. Let's go to number 5. It's asking about continuity and so I think if we're dealing with this type of problem, why don't we just step through continuity conditions and have everything laid out in front of us, and then we can answer these questions without having to do any additional work, right? So for number 5, we know that there's statements about continuity, so why don't we just step through continuity conditions one by one, and then let's compare our answers once you guys get a chance to show all your work. So remember your continuity conditions. Does a point exist? Does a limit exist? And does a point live where the limit lives?
Yeah, that's 6.
Hmm?
Or it's 6, they did.
Yep, it does, yep. So go ahead and try this full problem. I'll walk us through it. Okay, so second condition, one limit statement, or do we need two?
It's,
Just one, yeah. So if you see less than, greater than, then you would use 2, but here, the function is just up here. This is the point, so the point has no say on what the limit is doing. Okay, direct substitution. Factor. Reduce. Reevaluate.
6.
Make it 6. Okay, so it passes. So if it passes, that's the only time you look at the third condition. Okay, so make sure that you don't do the third condition unless the second condition passes. If the second condition fails, we know what type of discontinuity that we're dealing with. We're dealing with non-removable. So we know that this can't be non-removable. We passed the second condition. So the third condition, let's see, let's practice writing out what I want you to write. Is this a true statement? Yes, so all 3 conditions pass. What does that tell us? Our function is what? Continuous. Is it continuous everywhere? It could be, but we're only testing what? At x equals 3, right? So make sure that we're not guaranteeing continuity for the entire problem, for the entire graph. We're just testing one specific x value.
But
yeah.
Part 3 says like if you guarantee that the line x equals 3 is a vertical asymptote.
Oh, sorry. The 1, 2, and 3 doesn't match up with these here.
Oh.
I'm just going through a continuity condition. Now we're going to go and check to see which one of these is true. Okay. So it says which of the following is true. Circle all that applies. So limit does not exist. True or false?
False.
This is false, right? So we're not going to circle that one. F of x is continuous at x equals 3.
True. Sure.
True. X equals 3 is a vertical asymptote. False, because we know at 3 there's a what? There's a hole. Yep, you see that 0 over 0. If it was 10 over 0, 8 over 0, then you know there's a vertical asymptote, but that's not the case, right? Okay, any questions? Okay, page 6.
Number 1's just like finding the point on that graph.
Number 1.
Or like part 1 for the.
Oh, first condition?
Yeah.
Yeah, first condition is just always finding the point.
What would it be like number 2 or 2? What would it be if it's like non-removable? What would the answer be for the limit? That makes sense.
Oh, you mean if the okay. You're asking if the limit doesn't exist, or
Yeah, so that would be non-removable.
that's right, that will be non-removable, right? Right. We can skip number 6. Let's look at number 7 here. So this is kind of like a rear or another this is another way that they are presenting a problem that involves IVT or intermediate value theorem. So it says if f of x is continuous on the interval from 1 to 8, so we know that there's no sudden breaks here, even though we're only given 4 order pairs, we're given very limited information. We know there's no sudden asymptote or hole or any jump. It's guaranteed to be continuous because they're telling us that. And some value of f are given in the table above. Which of the following must be true? Okay. So can we guarantee that there's going to be a y value of -3 somewhere along this interval? So here we're starting off with a y value of -2. We go up to 4. We go up to 10, and we go slightly down to 6. So along this path, can I guarantee there's a y value of -3?
No,
All right, why no?
because like the Y values keep increasing.
It keeps increasing. Right now, it's possible that I could dip down to -3 that we don't know about. But based off of these values, we can also create a situation where it doesn't even touch -3, right? So this is possible, but it's not guaranteed. So which of the following must be true, right? We know that this can't always be true because we can already create a situation where it's not going to always be true. Okay, so basically this is a kind of like a another way of applying IVT. F of x equals 0 has a solution on the interval from 1 to 8. Can I guarantee that? Or
No.
a y value of 0? Yes. Okay. Why yes? Yes. If I start at a y value of -2, and if I go up to a y value of 4, I got to hit y value of 0 somewhere along the way, right? Because it's continuous, right? We know it's not going to all of a sudden skip over 0. So this one is true. Circle all that applies. So could be more than one answer. F of x equals 9 has a solution on the interval from 1 to 8. Yes, because we can see from 4 to 10, there's definitely going to be one solution. From 4 to 10, it's got to hit 9 on the way up, and it's got to at least hit 9 once on the way down from 10 to 6. Now, obviously, there could be more than that, but we're just trying to see if it's even true. So here we can actually guarantee how many solutions here.
2 gets to go back down.
Yeah, because it goes back down, right? Here we can guarantee 2, but it's only asking for 1. But I want to kind of show you that, if we wanted to guarantee 2, we could guarantee 2.
So what did the intervals tell you? The 1 on the 8?
That they tell you that we're starting at the x value of 1 and we're ending at the x value of 8. Right. If it tells you interval from 3 to 8, then we got to only look at those order pairs. Okay, but these are x value intervals here. Okay, yeah, so I see what some students are doing here. I see some students may look at the 1 and 8 and think that, well, 0 is not between 1 and 8, which is true, but keep in mind, right, that this is the y value here. The interval that they give you is always going to be the x value. So we don't want to compare x with y because that's not going to line up.
How I was thinking is like I thought it was a coordinate at first.
Oh, right. So yeah, anytime you see a solution on and they use brackets, that's usually an indication that they're talking about the interval, right? Because if it's an order pair, it will be both being parentheses. Yeah, but yeah, but sometimes it's also possible that they give parentheses. So it is a context issue, right? We have to kind of look at it and realize, wait, is that an order pair or is that an interval? Here, I messed up on the instructions here. We're gonna create 2 sketches. Okay, so we'll create a sketch. So let's do number 8 together, and then I'll have you guys try number 9. Okay, so number 8, sketch graph. Okay, now obviously everyone's graph could look a little different, but let me just talk about go through it one by one. So here, limit as x approaches -infinity. So that means I'm asking about how the arrow is behaving as I exit from view, right? Is it going up? Is it a horizontal asymptote? Is it going down towards -infinity? So here, whatever your graph looks like, you want your arrow as it exits from view, it's going to flatten out at -6. So it's okay if you have your graph cross through a horizontal asymptote. As long as your arrow ends up towards -6, that's what's most important. Okay, so -6, here's my y value, -6. I'm going to have it off the grid here just to show that's where I want to end up. Now, this is a horizontal asymptote, but it doesn't restrict a graph. So if your graph ends up crossing over the horizontal asymptote, that's not an issue, okay? The asymptote is only to direct what the arrow is doing. It's not a restriction that the graph can never cross. So I'm just going to have my graph show that horizontal asymptote. I don't know exactly what's gonna happen. Beyond that, I want to move that graph elsewhere, but you can have it below, you can have it crossover, it doesn't matter. We just want the arrow to flatten out as it exits. Okay, so that's, I took care of that first property. Okay. Yeah.
So whenever the horizontal asymptote, like it'll be like x to negative infinity or x positive infinity, whenever
That's
the
right.
vertical asymptote would be equals to positive infinity.
That's right. That's right. Yep. Good. Yeah. Anytime there's an equal to infinity or equal to negative infinity, you know that's a vertical asymptote. If it's limit approaching infinity and it's equal to a number, that's a horizontal asymptote.
It's okay if it goes off the grid.
Yeah. Yeah. Because we know that the arrow is going to head off the grid anyway. So I'm just kind of saving myself more room to work over here. Okay. Approaching -4 from the left side of -4 equals -3. So it doesn't have to be a full limit, but it needs to be at least true for one side limit. So at least from the left side of -4, I want to go to -3. I just want to make that connection. Now, this could be a hole, okay? In fact, well, that's fine. Technically, maybe it's better to leave it as a hole in case there's a point that is defined elsewhere, but I don't see any other -4 here, so I should be okay. Okay, so I'm going to just make that connection there.
So could you make it a full limit, or do you like right now you just have to make?
Right now, I don't want to make it a full limit yet. I could, but I want to make sure that I'm not conflicting with something else. Because if I create a full limit, that I may end up having to erase it because something else is conflicting with that. Okay, but at least I can check this off, right? Approaching -2 is equal to 1. Now this is a full limit, so that means as I know that my target is -2, 1. That's my order pair. And I'm going to make it a full limit. I'm going to put a hole there because I don't want to conflict if there's an order pair elsewhere. Okay, h of 0 equals 2. Now that's just the order pair here. Limit as x approaches 0 from the left of 0 equals 2. So
It's connected.
yeah, I can just connect this if I wanted to. Limit as x approaches 0. So the limit does not exist. Sorry, that's a D and E, not a 1 and not 1. That's not an O. So that means I can make this an asymptote. I can make it disconnected, or I can just leave it blank. Okay, so I'm just going to leave it blank for now and see what else I can do. Okay, approaching 3 from the right is equal to -4. So 3 from the right is -4. So I'm going to go to my order pair, 3, -4 here. I'm going to extend. I'm going to leave it as a whole. I don't know what else is. I think that's a safer play because if there's an order pair later on, I can fill it in. I mean, you can fill it in, but then the point may live elsewhere. So I like to always start off with a hole. Approaching 4 is equal to -infinity. Okay, so sorry, I think I extended that a little too far. I didn't mean to put the force so close to that point there. But I know that this is telling me what's happening here.
Vertical asymptote.
Vertical asymptote. And what does that -infinity tell me about the behavior of the graph? Okay. Just one side or both? Good. So when you see that -infinity, that means both sides. Okay. We need both arrows are going to move towards the asymptote.
So you connect the arrow to the limit.
I'm sorry.
Connect the arrow to the limit. What's that? Side.
Yeah, I'm moving the arrow closer towards my asymptote. Yeah, both arrows. I need both arrows because of this statement. Okay, limit as x approaches 8 equals 3. So my limit exists. So I'm gonna make that a hole. But I gotta extend it from both sides. But maybe I'll just do this. I'll just make these connect. You don't have to, but Okay, now what is this telling us?
Horizontal asymptote at 8.
Good, so that means when I leave the grid to the right, I want my graph to flatten out at y value of 8. So I'm gonna just have a dotted line at y equals 8 there, just to indicate. So whenever you do horizontal asymptote, maybe it's best just to do the dotted line off the grid, because sometimes I see students, they put it in the grid and they feel like they can't cross that line, and then it kind of restricts what their graph can look like. So just know that your horizontal asymptote is really going to impact just what's after. It's not going to impact what you see in front of you. So you can, if you want to, just put a dotted line afterwards. That way you're not having to look at a dotted line in the middle of your graph. You don't have to, it's really up to you. So I could do this. I could have the graph do this, or I could just have it go straight. I'm crossing it through just to show you that it's okay to cross over a horizontal asymptote. The asymptote is really just to tell us it's going to help guide the arrow towards the end. It's not a restriction that the graph can never cross.
So you draw it like that?
Yeah, or you can draw it like this. I drew it this way on my other graph. All right, as long as you have it, the arrow flattening out somehow towards the right along that dotted line, along y equals 8, that's what we want.
You don't connect the point at 0, right? Because it does not connect.
Right. So on my other, this is my other version here, I had it going pick up from a different point and went here. So I can either do this, or I can just leave it blank and not have anything show up here. That's fine as
Do
well.
you keep all your limits as full standard?
That's my preference.
Okay.
Just because if something else tells me to fill in the hole, it's easier for me to fill in the hole rather than putting order pair and realizing how to erase it later.
Okay.
That's just my preference.
You said you recommended like doing the order pairs first, right? Like
Yeah,
orders.
yeah, if you want to, yeah. But I think now you're right. Order pairs can help you. Is the easier thing to do, right? First. Okay. Any questions here? Right, you guys want to try number 9? See if you can sketch your graph first. Oh, let me ask you this. What if for J it says limit x approaching infinity is equal to negative infinity? What if it says negative infinity here?
Horizontal invert plus.
If it's approaching infinity and if it's equal to negative infinity, it's telling us what to do with this arrow. What do we do with this arrow here? We make it go down. Yeah, we just make it go down. So if its limit as x approaches that means that as we follow the arrow to the right, that there is no horizontal asymptote, but the graph is going to go down, so it's going to do this.
Oh, so the horizontal asymptote is still do this.
That's right. There is no horizontal asymptote if it's negative infinity. That means it never flattens out. It just keeps going down. Or if its limit, let's say limit x approaches negative infinity is equal to positive infinity. And how would this graph look? Yeah, it will go. That means I'm going left. And if I follow the left arrow, what's happening to my left arrow? It's pointing up. So whatever the graph looks like, it's going to end up pushing up. Does that make sense?
So there is something like that in our test.
Huh?
Would it be something like that in our test?
Yeah. So just know that if you're approaching negative or positive infinity, that this here is telling you how your arrow is behaving. Is it behaving towards a y value? Is it going up or is it going down? Right? So we need to be able to do that as well.
Also, there's 2 different holes.
Yeah, that's the way I did it, but if
Okay.
you can, I mean, you could go back and put a point there and a hole there. Again, anytime I see a limit, I'm always gonna put a hole. It's just, I find it, yeah, I just would prefer to erase. I would prefer to fill in later rather than having to erase it. Oh, God. If I realize there's something off about my graph. So my go-to is a hole if there's anything dealing with limits. Now your graph may look different than mine, which is fine, especially over here, right? Anywhere the limit doesn't exist, you have options. You can have it end here and pick up elsewhere. You can have vertical asymptote coming from the other side if you want. We just can't have both of these branches headed towards the same y value. We just can't. That's the only thing we can't do. Okay, this tells us limit does not exist. Okay, how do we do with the graph? Yeah.
So what is this like? X negative values do not exist. Can you put the hole like anywhere? Or
Yeah, you can put it anywhere. Yeah. We just don't want the graph to do this, right? We just can't have both arrows headed towards the same y value. Anything else you can do. Yeah. Yeah.
Something for the, at the vex, or the like 1 to 4.
Yeah, so that means as I approach 1 from the right side of 1, I wanted to approach -4. So I have it here. That means my right-handed limit is going to approach -4, y value -4 as I approach, as I move towards 1 from the right side. And so,
I couldn't.
oh, okay, yeah, it's a 1 with a plus sign here.
Yeah, I saw that. I just didn't know the 4 wasn't.
Oh, got it.
It's like,
Yeah,
there's
yeah,
like a line.
right, yeah. -4.
and it must pass the vertical line test. Like
Exactly, yep. So after you sketch your graph, double check. I should not hit more than 1 point, no matter where I draw mine. Now, it looks like it's sort of here, but it's a vertical asymptote, so it is going to feel like, but technically, you know, every X value doesn't have more than 1 point. Okay. Why don't we do an IVT problem? So if you can turn to page 11, this is the quiz. This is a quiz review that from previous years, because in the past I had a second quiz. So this is on page 11. Try number 3. See if you can go through your conditions for IVT. Remember, you have to make a statement about continuity. You have to make a statement about your endpoints. You have to say something about how your target is between your endpoints. A good chance for us to see if we can write out in the form that we want to write it out. Okay. Yeah, class ends a little early today, so I'll make sure I get through everything. We know that there is a potential issue, right? Anytime we see a variable in the denominator, in this case, what's happening here? There's a what? Vertical asymptote where? X equals 3. Okay, so we know there's one issue across this entire graph. There is one vertical asymptote, but we got to check, is this going to cause issues with my interval? No, so we're good. Okay, so we checked. We did not see any issues, so we can make our statement about continuity. We can continue with our theorem. Make sure you specify the interval that you're working with. Our function is continuous from 4 to 8. We're safe. Let's move on to IVT. So first thing is we have to work on our endpoints because this is our target, right? This is our Y value target. And then these are our X value intervals. Okay, you obviously don't have to write this on the test, but I just want to make sure that we don't look at the two and try to compare the two with the 4 and 8, right? These are not the same. They're not referring to the same axis. Okay, so f of 4, insert 4 in, what do we get? 4 over 1, which is 4, okay. F of 8.
Or
8 over 5, okay. So 8 over 5 is like 1 point something, yes, 1 point something, right? So is 2 going to fall between 8 fifths and 4?
Yeah.
Yes, right. We're starting at a point below 2 and we're ending at a point above 2. We're going to be safe. Okay, so now we just have to go through our conditions here. Now there's a second part. The second part is finding C, but we'll do that for B. Okay. So we can say that our by IVT. Since
Pardon the interruption, teachers and students. The math testing site is down nationwide. We will not be able to do the testing today.
yes.
We will be switching to a regular bell schedule for today. Stay tuned for information about tomorrow. Thank you.
Oh, that's unfortunate. Yeah. So you mean test tomorrow then?
no.
Okay.
But if that the issue is
Kind
my
of messed up.
my test is Thursday, so I don't mind pushing it to Friday, but that just means another day of new material. So we'll see what happens. Okay, so f of 8 is 8 fifths, so we have a bit more time to do review. Yeah, I will give you a full class period, but the issue is if I'm pushing the test back, I'm adding another day of new material, right? Because I don't want to lose a day of instruction. So okay, f of 8 equals 8 fifths. 8 fifths is equal to sorry, less than, my bad. Less than 2, and 2 is between 8 fifths and 4. So it feels like I'm going backwards here, but I like to use less than, so that's why I'm always going to pick the lower value and go to the higher value, even though I'm starting at 8 and going back to 4. Does that make sense? So if you want to go from 4 to 8, you can. You just have to use greater than. Yeah. Okay, so since this is true, we know that f of C must be equal to 2 somewhere on the interval from 4 to 8.
Oh, so you're trying to confirm that FC was 2?
Yeah, I'm just trying to confirm that FC equals 2. So that's the first part. Okay. Any questions with that notation?
Where did you do the conditions at? Because I know.
Oh, conditions are here.
Oh, okay. You just didn't label them 1, 2, 3.
Right, I didn't label them. Yeah, I say my function is continuous, and then well, this is technically a condition because I'm showing that my Y value target is between my endpoint Y values. So now how do I find C? How do I find, now that I know that there is a physical location where the graph is going to hit a Y value of 2, how can I find that C value? Basically, how can I find that X value where this graph occurs? Good. Yeah, the function with 2. Good. So you're just basically taking your Y value, inserting it, and finding your X. Okay. So 2 is equal to X over X minus 3.
Let's find X minus 3.
Yeah, well, I like to put this over 1 and cross multiply, just so I can, that's my preference. Let's bring our X over to one side. 2x minus 1x is X. X equals 6. Now, is this X value between my interval? Yes, right. 6 is between 4 and 8, right? So this is safe. And also, this is a guarantee, right? Once we get past this statement, we should always get at least one location that's between the interval. If we don't, something didn't go quite right. Either we did something wrong with this statement, or algebraically we did something wrong. So, but this, once we get past this, it's a guarantee that we can find a location where there's an order pair that sits between 4 and 8 that has a Y value of 2.
So so there's two different answers. Different answers, like the one where we say 5 IVT, and the second answer is we find 6.
Yeah, so it says show whether IVT applies. That's basically this statement. Finding C is the algebra that you can use to solve for that X value. Okay, I think this one up here is great. Well, here, let's do this. I want to make sure that you guys. Where's my test packet? Okay, here it is. I want to make sure that we feel confident that we've gone over everything at least once. So on page 25, let's revisit page 25 again. Okay, evaluating limits algebraically, real numbers approaching infinity, one-side limit. We saw a really good example of that yesterday with the piecewise function and being able to match it up. And I feel like the page we just got done working on, page 11, this is also a really good example. So if you want to spend time working on this on your own, and then the answer is attached on the back, this is a really good smaller, shorter example of what you can see on the test. And so maybe I'll leave that for you guys to try to see if you can really feel good about that. Okay, so you'll see something like that. Evaluating limits algebraically with hole in the graph, applying methods of factoring, conjugating, common denominator. So basically review your quiz, right? So you're going to see maybe 1 or 2 problems that's similar to what you saw in your quiz. Identify limits of order pair from a graph. So we didn't do that, but that's the easier version easier than sketching a graph. So problem like on page 11, like number 4 at the bottom, where I give you the graph and I ask you what the limit is, what the order pair is. This is easy, right? You guys did this on the quiz as well. You guys were great at that. So okay. Identify limits and order pairs. Okay, we did that. Okay, sketching a graph given limit properties. We did 2 examples of that. Okay, use continuity conditions, categorize continuity, discontinuity, whether it's removable or non-removable. We did that today and yesterday. Apply IVT, we just did that. Okay, finding horizontal asymptote, we did that as well, right? We know that there's 2 asymptotes and it's the ratio of the coefficients if the degrees are the same. And then comparative growth rates, right? So remember, compare the growth rates. If it's approaching infinity, and if you have 2 different families of functions, we can decide whether it's either 0 or plus or minus infinity. So let's do this one again. We know that logs is slowest, followed by radicals, followed by polynomials, followed by exponential. Okay. I think students tend to have this a little bit, understand exponential is the fastest, polynomial is next. Sometimes students get confused between these 2. So I would say just this is alphabetical, right? So logs is slowest, and then radical is next. So in this example, right, what's in the numerator?
Exponential.
And denominator is radical. Which side is going faster?
Exponential.
Exponential. Okay, so we know that if my numerator is larger than my denominator, my overall fraction is getting what?
Faster.
Yeah, or bigger or smaller?
Bigger.
Bigger. So if it's getting bigger, there's 2 options, right? It's either going up to positive or infinity, right? So here, if we're deciding between these 2 options, then we can test what? Sorry, this should be x. My bad. X equals 100. Right? If I plug 100 in for x, I get e to the 200, which is positive. And then square root of 200 plus 1,000, that's also positive. So positive.
What would it be if like the slower one was on top of it?
Yeah, let's do an example of that. So limit as x approaches again, this only works for pos infinity. And let's say I have, okay, again, we're approaching infinity here. Numerator and denominator are completely different sets of families of functions that are nicely separated. The top is what?
Logs.
Logs. Denominator is radicals. Which one is growing faster?
The bottom.
Bottom. So if my denominator is growing faster than my numerator, what's happening to my overall fraction?
Going to zero.
It's smaller. It's getting smaller eventually because it's going to infinity. Eventually, it's going to approach zero because it's going forever. So that fraction is getting even smaller and smaller and smaller, headed towards zero.
Can you give one more example, like the finding horizontal asymptotes for radical?
Yeah, look at that. I'll put this on the back if you guys want. And yeah, so find horizontal asymptotes for y is equal to okay, so anytime we're doing horizontal asymptotes, that's the same thing as a limit approaching infinity. So why don't we just go through our limit statement and see what happens. So we know if we're dealing with infinity, we always compare degrees. So what's the degree of the top? 2, right? Square root of 4 is going to be 2. Okay, so and denominator is also 2. Degrees are the same, so therefore, so yeah, negative root 3 over 2. So that's one of them, right? That's one horizontal asymptote. What if I'm going from the other side? What's going to happen here? Oh, actually, you know what? This one is not going to have, sorry, I did not give a good example here. Yeah, this, it'll only, I was trying to give more variety here, but really it's only going to work. Sorry about that. Okay, scratch that, sorry. So for approaching infinity, for this one would give me degrees are the same, and I have root 3 over negative 2. Let's look at it from the other perspective. Again, it's going to be negative root 3, or we know the ratio is the same, right? Root 3 over 2, but let's just test a value to see what the sign is. So if I plug in a large negative value into the numerator, what sign am I going to get? Positive. If I plug in negative 100 or negative 1,000,000 in for x, what sign am I going to get? Positive. So positive or positive is positive. So I'm always going to get this flipped sign, right? Whatever the ratio is, there's going to be a positive, there's going to be a negative. So my two horizontal asymptotes is going to be y is equal to root 3 over 2, and y equals to negative root 3 over 2. But there's only split asymptotes if there's square roots involved and the degrees are the same. Okay, so okay, you come up and get your phones. Tomorrow we're going to start our next unit, and right now I'm still going to say the test is Thursday, but it could be pushed to Friday. Okay.
What only the denominator was on the bottom? Higher degrees on the
What do you mean? Like,
if the horizontal asymptote, like you're trying to find it in the higher degree on the bottom.
then it's going to be 0.
Okay.
Zero.
And then it was on the top, then that's.
If it's on the top, yeah, if the higher degree is up top, then you got to test it.
Okay. And we're just saying, just take a photo.
Ratio.
Maybe could we possibly like